FRP strips on the surface. So we have tested these beams with the different combinations, and in most of cases we found that observation for that found that debonding failure of the FRP system was there. This is for 70-30% hybrid FRP system. Here we are combining the response of all, comparing the control beams, and you see that there is significant improvement in strength up there with the just 2 bars of 8 and 10 mm diameters were tested, and there is a 70 and 30% combinations. Although this strength has been observed with the debonding mode of FRP failure, it means that full strength of FRP rebars had not been utilized sufficiently. So this is the debonding failures. In fact, only 2 minutes are there, but there are some other things I've shown that this application have also shown application of ductile fiber reinforced concretes. For in addition to FRP system, so far in NSM class, we have shown the application of ECC material as a substitute for ECC, as a substitute for FRP, and for frames and beams, and it found that a very good improvement in strength and ductility has been achieved for this combination. See, this is the advantage of here ECC material. See that in normal FRP concrete just going for peak and then strain softening branch starts here. But in case of typical ECC material, we have strain hardening branch starts in between the peak, and that is the first stacking and peak, and then strain softening branch starts from the peak one here. This strain hardening branch is not there in typical FRC system, and that's advantage of ECC material which can be applied for external strengthening of this material, because you are not looking for whole structure of this material, but you are looking for this ECC as a precast element which can layer or plastic hinges locations, and then we can get the sufficient strength as well ductility. So the typical FRP material plus ductile ECC can also show a very good improvement in strength and stiffness. They are typical beams have taken under enforced and over enforced beams with different loading combinations. This we have taken here ECC and a particular plastic in location. Then here we have taken the ECC as layers, and we see that response is found to be very good. And then we are picking normalized strength parameters and then deflections. And say for over enforced plastic hinge of length of 600 mm, we find a very significant strength improvement. And we also saw that there is significant amount of ductility also available in system. And similar observation we have made for, and it's also for ductility failure, except for although we got a 600 mm plastic hinge length while giving very good strength, but there is a localized crack developed at time of failure. In other cases, there are multiple cracking has appeared. Similarly, for under reinforced beams also they are getting this. There is much better response is achieved here in case of under reinforced plastic hinge of length 600 mm. For other plastic hinges, we are not getting significant improvement, but for 600 mm length of plastic hinges at put at mid span, we are getting very significant strength. There are some mode of failure. Similarly, here going for layers concept, external layers, we are using the strips of ECC and putting in external layers, and there also we are getting significant improvement here. This is a contour beams, and there we are looking for 50 and then for 70 mm thickness of layer. And see that this length strength improvement is about 8.31 times the contour beam. There is significant improvement there. Just for 5 and 50 mm is thickness of ECC layer. This is for similarly for over enforced span beams. We are not getting that improvement advantage as in case of under enforced beam, but still there is ductility is improved here in system, even for over enforced beam. Now come to the here, so there is a frame here. This is typical. I just want to skip here. Here just to show that in beam column connection, a typical frame we have structure we have taken, and just to show the demonstrate effectiveness of ECC at the not for full length. We have just compared 3 kinds of frame structures we have taken. One is made of completely DFRC, one is pure concrete, and one in case we are just putting the ECC at a static location, that is near plastic hinge zones. And then we design the 2 kinds of ductile drilling head, one per IS 139020 and one category 2 frame are designed as per IS 456. And we are showing that in even the frame structure designed as per IS 456 detailing, we are finding response of ECC is found to be very good. So this is detailing as per IS 1392, and this is for detailing as per IS 456. We are loading spans here, structures, and say that for structures were designed for IS 139022. This is response of this structure. Middle one is response of structures of frame structure with the ECC at a specific locations. And second case we are saying that is response by detailing has been done as per IS 456 only, and this is for fully ECC beam frame. This is contour concrete beam, and this is a control frame, and this is the one where we are using the ECC at specific locations only, and we are saying a very good response, correlation has been obtained, even achieved there, maintained there. So these are for different types of frame structure, category 1 and category 2 frames. We are finding that here for definitely the ductility factors are taking 3.78. In case of category 2 frame, ductility factor is 3.37 frames, which is so that is designed for IS 456 only. Here this frame is designed for IS 1392. So there is not much difference there. In fact, I just want to show a conclusions here. With time limited here. We have just proved that we try to make the FRP system, develop a FRP system, normal FRP system, and a pseudo-ductile FRP system. We utilize that FRP system as a strengthening, especially NSM part, and then it's tested on RC beam, normal RC structures, frame structures, and ECC beams, and found that this near surface mounted bars FRP systems have found to be very, very effective, especially for definitely for external strengthening of system, and definitely till today's research, we can say that is very found to be very, very efficient technique, and you can utilize. In fact, there is a lot of research had to go still, because one of the mode of failure, that is debonding, is the main failure mode that is coming into picture here. If that could be reduced by further research work of developing some mechanism, then you can effectiveness could be further improved. So this is still research going on, and further future research. We have already got a DST project in this direction to use this material and this technology for masonry structures, concrete as well as clay burnt brick masonry structures, and that our team is working on that. And then see, finally, one important thing that we got for developing design approach and testing with the that is experimental results, we found that conventional definition of section being under enforced or over enforced based on balance ratio that we design usually for force is not consistent with experimental result for engineered cemented composite beams. Hence, more experimental investigations are required to investigate the correlation between flagella crushing strain and crushing strain from YRGS. Although we have modified this equation, developed the equation, published also, but still I feel by personally feeling that we need a detailed investigation on this aspect. That's why I'm highlighting that, and definitely for FRP reinforced ECC beam structures, this concept or that expression for balance ratio or actual enforced ratio that we are getting for defining section under enforced over enforced need to be modified. Definitely, there are some optical differences, and this work has been in fact continuing, and we are getting different projects, DST, EDC, PKD, such collaborations, RTB lab projects, and ATB lab projects, and CSI and others. So this outcome, in fact, based on different projects, more design guidelines, etc. I have not been able to put in there, but this has been already published, and this is some of the references there. You can look in that. Thank you very much. Professor Singh.
I'm Dr. Hematma Vinay from a particular beam in which that groove was shown for retrofitting. Now mostly the retrofitting, we have seen that normally the structures or structural elements become deficient with respect to both the longitudinal and the moment as well as the shear.
Right.
So I just wanted to know that, okay, in this particular case, one is that those two grooves have been shown. So one is that how much anchorage is given to the column, and second is that what about the shear reinforcement, or how do we increase the shear in this particular case?
For shear reinforcement, you have to put these grooves on the side. Externally, you are going for it. So here is, in fact, we are showing for flexure only, yes, not for shear.
Yes.
But for shear, in fact, similar kind of only thing that you have to maintain design. Actually, we are looking at recently we have published a paper on ASC also, and our undergraduate student done a detailed work on by just we have experimental results, and plus recently it might be online, it's applicable that. I think I can recommend you people to read that paper. So there your Baker's model we have done to just optimize what should be the groove size, what should be the groove spacing, and what should the groove be. This should be that should we have to look into pattern. That's affect the response of the NSM technology. But as far as shear is concerned, definitely you can put this in place of flexural zone. Usually talking about a tension zone you are putting here. You can put on side of the beam. That will enhance at the optimum spacing. That's design guidelines there, and then that will improve your shear strength.
And how much is the anchorage just to be given from the beam to the column? Normally, like in simple reinforcement steel, we go for 50 deep, the diameter of deep.
See, this is I for anchorage concerned, you have to see that if this portion is accessible to you, it will better that the grouping can be put in the nearest column side. Suppose I am putting the group, it will better you can make some grooves in the inside the column and anchor that one. But in fact, suppose you are getting this concept even applicable for FRP sheets also. There we are just like a curtailment of plate we are doing for optimize or saving the materials. We can cut the plates, but there we are not looking for. But in SM technology, we can put, you can make a groove, and so easy that because here is efficiency come of this LSM bar. We can make some grooves in the column, nearby column, and we can just start that one. One input that one, other one. But ultimately, you have to put this whole thing with the epoxy or resin materials in the group up to optimal size. And that idea is that will help debonding, prevention of debonding.
Good morning to all of you. At the outset, I will record my gratitude to Sandeep, and it's the dictate of Sandeep for which I am here. And the things which I'll be going to present that has definite connotation in respect of the entire structural engineering, but because of the fact that there is ample possibility of the listeners being heterogeneous and not being very much exposed to the materials part of the steels per se, if it is a rebar or the steel as a structural material. But most important point is that right at this particular moment there has been a tremendous upsurge in the entire steel activities with an eye to the applicability of the new generation steels in the structural engineering. So I'll be talking about a little bit of the new steels which people these days talk about. And the last paper, one very important thing has been verified, or I would say that advocated, that is that whenever, even if you take a concrete, then you find that the steel as such, that takes a huge amount of load, and also that the 45% in one particular case, the 55% in another particular case, and also because of the shape of the steels. And another important point is that the question of the steel being taken too much of load, and then the question of buckling is also there. Now suppose if that is not there, I mean if at all the steel is such that I don't want to have that kind of dimension, but yet it is capable of taking that amount of load, that's precisely what we look for. I mean, as a material scientist, we look for that. Now I would say that the way I see the structural materials, which are primarily the concrete or the structural steels, whenever I say, then these are the structural steels which I'll be talking about, just to tell you. But I would like to start this way, that I mean, what are the normal things which we all expect from the structural steels? Whenever, not only the structural steels, for the structural materials per se, right at this particular point of time, in this 21st century, we want that any material to be employed for that matter, any particular purpose, that has to have a very high durability, it has to have a very high reliability, it has to have the fabricability, in the sustainability is another important thing, and then of course the low cost. I'm not going for the cost by default will be made lower. Now whenever we talk about the durability of any material, be it concrete, be it the structural steels, then we have to talk about the time-dependent properties of any material. And whenever we talk about the time-dependent properties, the three important aspects of all time-dependent properties are there. One is the creep, which is a time-dependent property at a higher temperature. The other one is the stress corrosion or the corrosion properties. And the third one is your fatigue properties. The majority of the failures we find within the structural engineering, they originate from the fatigue. And also there are certain aspects, but again ultimately you can make it convert into the fatigue failure. Then whenever we talk about the reliability for any structural design, always you have a stipulated period. Okay, I'll be giving it for 100 years of stipulated life. So whenever you say, then it is very important that you know on the basis of a fail-safe design concept that it's not going to be failed within that stipulated design period, which is the concept which is being used these days, that will also have certain things to do with the steels. And then the fabricability and then the sustainability. Sustainability is one very important thing. It can be looked into from different angles. I'll be showing you how can we look at it. As I've already told you that the creep, which is your normally if I talk about creep, I will not explain why. The sciences I will not explain, but whenever we talk about creep resistance for any material, then always you will have that one matrix will be there and one refractive dispersoids will be there. There are reasons for which the creep properties will be always higher if I can have a refractive dispersoids in any matrix, for that matter in any material, be it ceramic, be it polymer, be it metal. And then the grain structure, the final will be the materials, then there are certain advantages. The final is the components, constituents of any material. In the stress corrosion resistance, specifically in steel, or the corrosion resistance, they are dependent on the grain shape of the material and the environmental condition. That I will be coming later. Why do I say it? And then fatigue, whenever we talk, there is an inflation and growth of fatigue cracks. That is much more important for all kinds of structural applications, which we have dismally neglected till recent past. Now, the fail-safe design. Whenever we talk about the fail-safe design concept, one very important point we have to take in our mind, that in today's scenario we are a little bit pragmatic. We all know that we deal with crack bodies. No bodies in this universe is there which is not containing any cracks. So the cracks body are there which we are working with. And if that is there, then it is much more important. We don't bother about how many cracks are there. We simply bother about what is the size of the crack, which is a load, and what is that stipulated life, and whether these cracks are capable of withstanding those things, not growing to fatality. So that is precisely what this fracture toughness property of any material gives. And depending upon the condition of the stress situation, it can be a plane strain fracture toughness, where the strain in the third dimension is infinitely, very small. So naturally, for a thick section and then for a thinner section, the plane stress fracture toughness is of importance. So naturally, we don't talk about these days. The materials people, we don't like that the people talk about the yield stress, tensile stress. The design should be based on the fracture toughness of any material, because that ultimately gives you the fail-safe design. So therefore, that is important. But by default, the fracture toughness is again determined by the fatigue, crack, growth characteristics. Even if you talk about any particular structural component, even if you do not do everything is so innocent, then you will find that there will be temperature fluctuations, there will be, many fluctuations will be there, the temperature in ambient situation, and then you will find that this is a fatigue situation. And this fatigue situation, the way we used to understand, even the material scientists, there has been a sea change in that. Now, because of the structural engineering part, we today talk about the ultra high cycle fatigue and a very complicated cycle. And even if the material contains a very short crack, the crack growth characteristics of an ultra small crack is something different from what we used to know some 10 years back. So this is another important area where the people should know. So the fatigue crack growth characteristics. Now this has happened since the advent of linear elastic fracture mechanics. When the fracture toughness used to be determined by this K1C, which is a stress intensity factor just ahead of the crack tip, and then again we have more pragmatic, because we also understand that the crack tip, the stress singularity doesn't really happen. At the crack tip there is some plasticity, so naturally elastic plastic fracture toughness is what is important. So whenever we go for the finite element modeling of any particular steels for any particular application, we really go for Jane-Ziegel method, and we think that this is much more a practical proposition. And then of course the other important point is that if I talk about the fracture toughness, this is of course may not be that interesting to the listeners here, but that is the microstructure which ultimately determines everything of any material. Then the sustainability. The sustainability, while you talk about a particular structural material, the sustainability is another very important thing. The resistance to degradation, we all talk about the chloride and this corrosion of river, what it will be that particular material. People have been trying, you have been trying quite a lot with different materials. and then I will also project some material for you, but I don't say that you use it, but I simply say that there is logic for those materials being considered. But one important point which we must not miss in today's scenario, whenever we talk of sustainability, we talk in a global terms. These days we don't talk about the sustainability of a material on short-term basis. This is a global concept. The life cycle assessment rights is the part of a particular material. Since when it is totally destroyed, what is that which is ultimately hampering the ecological balance of the universe? That is precisely what we talk about, or what we really mean by the sustainability of a material. So that's why a material, even if it's structural material, be it concrete, one very important point what we should all remember, that concrete is the second largest consumable of human beings. It's a more than 10 metric tons per capita consumption is there. The next to water, it is the largest consumable of the human being. So therefore, there is a great threat that unless we have really something to do with such kind of structures where we make use of concrete, durability, either in terms of durability or in terms of recyclability, then there can be a catastrophic failure in our civilization drive. So this is the important point. And then any new generation structural steels must have to have some fabricability. That means the deformability as well as the weldability.